Morning, everyone. Let's pick up where we left off last time, talking about alkanes, these single bonded carbon chains, and now we're starting to add accessories. So the accessories, you do need to say where the accessories are on the chain. It's not enough to just say, oh, it's chloromethylpentane, for instance, for this one. You have to say that it's on the 2 and on the 3. Because if this, let's say that it was 3-chloro-3-methane, the chlorine was on this carbon with this methyl, it would have totally different chemical properties, okay? So you need to really specify. We always want to count when we're dealing with these alkanes, you want to count from the side that will make the chain, or the accessories set at the lowest number. So let's do a couple of these because I think it jumps right into cycloalkanes. So we'll do a little bit of practice with this. Actually, I'm going to drop that H. And actually, I need to drop this H here too. Sorry. Give me a second to write it out before you fully copy it, okay? Because I'm sort of adjusting as I go. Okay. So I want you to name this thing. You are going to name it. Well, yeah, I'm going to have you name that. So try it out. And if you don't succeed, that's okay. We'll do a couple more, but I want you to at least try. Find the longest carbon chain, name that, circle the accessories, label the carbons, and yeah, go from there. Okay, so for this one, the first thing we need to do is find the longest single carbon chain, and everything else becomes an accessory. So just because it's written with this chain on the horizontal doesn't mean it's the longest carbon chain. A lot of times what I see is people go, oh, there it is. That's the main carbon chain. Well, how many carbons is that? 1, 2, 3, 4, 5, 6 carbons. Okay. What if I went this way instead and then over? 1, 2, 3, 4, 5, 6, 7. 7 carbons on the main chain. You want to try and pack as many carbons on the main chain as you can. Remember, because these are single bonded, these are free to rotate. So it's sort of like you can even think about these two being over here and this guy being pointing down or something, right? So this is the main chain. So it's going to be, you guys are going to have to start getting used to sort of seeing these in three-dimensional space where things can rotate. At least they can when they're all single chained. So that's my longest carbon chain. Where are my accessories then? If this is the longest carbon chain, it's going to be anything that's sticking off of that that isn't just a plain hydrogen. So this is an accessory. This is an accessory, because if this is the main chain, this is sticking off of it. And then both of these are accessories. So I have 2 methyls. I've got 2 methyls and 2 chloros. All right, when I have more than one accessory, I have to call it like dimethyl or dichloro, okay? You have to denote that you've got 2 of them. If I had 3 of them, I'd have to say tri. So I guess let's first just put the longest chain in. So 7 is hept, and they're all single bonded, so this is heptane. Now I need to start adding the beginning parts. So I've got some chloros, specifically 2 chloros. So because it's 2, it's going to be dichloro. I've got 2 methyls as well, methyl. And because there's 2 of them, it's going to be dimethyl. What comes first in the alphabet? Chlorine. Chloro comes before methyl, so we'll do that. There are 2 chlorines. So it's not enough to say 2 dichloro. You actually have to say 2, 2. So there's one on the 2 and another one on the 2, dichloro dash dichloro dash, actually, I don't know why I'm saying 2, 2. It's not even on the 2. Where am I? We have to number the carbon chain. Okay, so do I want to number it from this direction or do I want to number it from this direction? Well, if I number it from this direction, my first accessory starts on the 3. 1, 2, 3. If I start from this direction, 1, 2, my first accessory lands on the 2. The numbers will be lower. So I'm going to name this or label this one, and this, I don't know where I am this morning. This should be a 3. 1, 2, 3, 4, 5, 6, 7. Okay, that will allow the accessories to land on the 2, the 4, and the 5. In the other direction, they would have landed on the 3, the 4, and it's 6. So it would have been lower. Now I can label where they are. So chlorine is on 4. So it's 4, 4, dichloro. And this is a dash here. It's little details. Sorry, guys. I don't know where my brain is. 4, 4 dash dichloro dash. We've got the methyls. There's a 2 and a 5. So dash 2, 5 dash dimethyl heptane. 4, 4 dash dichloro 2, 5 dimethylheptane. Commas come between numbers, dashes come between numbers and words. Okay, so give yourself a note there that you want to be putting commas in there and dashes in between numbers and words. If you have a word and a word next to it, like the methylheptane or the dimethylheptane, you just smush that together. So let's do another one in this direction where I will give you the drawing and you have to tell me what it is. Give me a second to write it out. For good measures. Okay. That's the structure. So I want you to name this thing. There is stuff in this upper right-hand corner here too, so make sure you take that into account. Just erase that. Okay, so hopefully you didn't fall for my nasty tricks a second time. So finding the longest carbon chain. Here, not straight across, we're gonna kink it up. Okay, so this way, over and up. 1, 2, 3, 4, 5, 6, 7. If you're wondering, well, could I have gone 1, 2, 3, 4, 5, 6, 7, because that also would have been 7. You don't want to have an accessory off of an accessory. Okay, that would have made it like an ethyl group with a fluoro off of it. So let's keep the accessories just coming off the main chain. So accessories, we've got a fluoro. We've got, this is an ethyl. So 2 carbons coming off the main chain that are connected to each other like this is an ethyl group. Specifically, just an ethyl. And then over here, I've got a methyl and a methyl. So we would say that that's dimethyl. And they're both attached to the same carbon. So now we need to count. How do we want to count? If I go this way, my accessories, okay, 1, 2, 3, it'll be on the 2, the 3, 4, the 5. I like that. The 1, the 3, and the 5 versus 1, 2, that would put it on 3, 5, and 6. The numbers would be higher. So you always want to put it in order so the accessory numbers are lowest. If you want to, you can always name them both ways and then just see which one where the numbers are lower. So this is going to be carbon 1, 2, 3, 4, 5, 6, and 7. So again, 7 is heptane. This is a heptane chain, just like the previous heptane chain, but this would have totally different properties because of its accessories. So we need to talk about the accessories. So list them in alphabetical order. I've got ethyl, fluoro, and dimethyl. And we'll go with the methyl, not the di. So I'm gonna put the ethyl and it's on the 3. So 3-ethyl. Okay, that takes care of this accessory. I need to do the fluoro dash, it's on the 2, so 2-fluoro. It takes care of this accessory. And then these final 2 here, dash, and they're both on, what did we say, the 5, right? So 5, 5 dash dimethyl heptane. So the name that you give, you should be able to take this name and redraw the exact structure, right? Maybe it doesn't have the kink in it, but you should be able to recreate the structure with the accessories in the appropriate area. That's how much information you want to give. Questions?
How do we know that it's an ethyl as compared to like a methyl? Is there like a chart to see?
Yeah, so remember how we named the carbon chains? So meth is 1, eth is 2, prop is 3. It has to do with how long the chain is. So this is just 1 carbon.
Okay.
So do you see how that's just a single carbon packet?
Yes.
With hydrogen, so that's what makes it a methyl. This accessory here, what is it? It's 2 carbons. So 2 carbons is the F.
You're still using
So if it was 2 carbon chains, it would be ethane, right? But because it's an accessory, that's why we give it the YL last name, or the ending. That tells us it's coming off of the main chain.
Okay.
If this happened to be 3, well, if this happened to be 3, then we're in a little bit of a different situation because we've got the fluorine over here. We'd probably still keep that as an accessory. But if it happened to be 3 and this was a longer chain, we would say that it's a propyl group. If it was a 4 accessory, a butyl. But usually you guys won't probably see anything longer than 2 carbon chains.
Okay.
So let's try going in the other direction. Oh, let's talk about cycloalkanes actually. Yeah. So remember, a cycloalkane is a ringed chain of carbons that are all single bonded to each other. When you have one substitute attached to a carbon, the whatever the accessory is, is placed in front of the cycloalkane name. So this is hexane, right? It's 6, or rather it's a cyclohexane because it's 6 carbons in a loop. What is this accessory? Cecilia, we've got 2 carbons here, so we would say that this is an ethyl, right? So for the name, we would just smush that in front of the cyclohexane. We would just call it ethyl cyclohexane. There's no number needed. I don't have to say it's on carbon 1 because we're just assuming it's carbon 1 because it's a cyclical structure. So we would always denote this as 1 and then in either direction 2, 3, carbon 4, 5, and 6. Okay, this always just ends up getting placed on carbon 1. Even if it's drawn in a way where like the ethyl is not in the up position, we still consider that carbon 1. It just makes it faster for writing. This can be true for halogens as well. So instead of, let's say this wasn't here. Okay, we've got our group and we've got over here, I've got a Cl coming off of it. I would call that chlorocyclohexane. Again, we would just make this the carbon 1, whatever the accessory is sitting on. So we've sort of already gone into this. But if we're naming alkanes, we have to, if the chain ends up being really 3 or more, we have to describe where it is. So like, you see how one of the hydrogens here has been transferred with the chlorine? So we would call this chloromethane. Why don't I have to say that it's 1 chloromethane? Well, how many carbons are there? There's only 1 carbon. So is it possible for this chlorine to be on a 2nd carbon? No, there is no 2nd carbon. So we don't need to denote the location because I know if it's chloromethane, the chlorine has to be on that main carbon. Same thing here. If I have bromoethane, there's a bromine on this ethane. Where's the bromine? It's always on like a terminal, right? If it was here, it's on carbon 1. If it happened to be over here, it would still be on carbon 1. It's the same thing, just flipped. Now, when I get to a chain of 3 or more, I have to say where the accessory is because the fluorine could be on this guy or it could be on the central one, and that would actually make a new structure. So drawing a structure, I think it's actually easier to draw the structure from the name than to draw the, to come up with the name from the structure. But again, people have different strengths and weaknesses. So if we want to draw this structure, we have this fun name here called 1-chloro-2,3-dimethylheptane. So what I like to do when, heptane again, when I like to draw these structures, I always start with, I start on my right side and I draw the carbon chain. So here we've got heptane. That means that it's 7 carbons, right? So it would be 1, 2, 3, 4, 5, 6, 7. I don't put my hydrogens in yet. I do that at the end. So once I've got my carbon chain of 7, I'm going to make it easy for myself and make this carbon 1 over here. Like, why would I make carbon 1 over here? I get to draw it. So I'm going to draw it this way. So I have a chlorine on carbon 1. So let's add a chlorine on carbon 1. I've got 2 methyl groups and there is a methyl group on carbon 2 here. CH3, and there is a methyl group on carbon 3 over here, just for space, CH3. Okay, so I've put all my accessories in. The last thing to do is add the hydrogens. So this carbon here has 2 bonds already, so he can only have 2 hydrogens. This carbon here has 3 bonds, so he can only have 1 hydrogen. This also only has 3 bonds, so it can only have 1 hydrogen. This is bonded to 2 other things, so 2 hydrogens. And then the rest don't have any accessories, so they go with what we're used to, 2s and then 3s at the end. So make the longest chain first and then add the accessories and then saturate it with hydrogen. Same thing says here, draw the main chain, number the chain, put your accessories or constituents, add the correct number of hydrogens to balance it out. So I want you to draw this guy here. 3 bromo, 1 chlorobutane. Start with the longest chain or the thing all the way over to the right. Okay, so for this guy, the longest chain butane is 4 carbons. So we should draw a 4 carbon chain. Sometimes they'll draw it like this. If you get real lazy like I do, they'll just draw it like this. You can do it that way as well. We need to number the carbon chain. Why not make it easy for yourself and just have the one on the left be 1. So 1, 2, 3, 4. And then we need to add the bromines and the chloros. So this isn't, these got shifted over for whatever reason. What's going on here, slides? Slide auto-corrected, very strange. Okay. I might end up pulling up the PDF slides if that happens too much. Okay, so we count our carbons. 1, 2, 3, 4. The chlorine goes on the 1. The bromine goes on the 3. Then you need to fill in your hydrogens. So this gets 2 hydrogens because it already has 2 existing bonds. This gets 2 hydrogens because it has 2 bonds. This gets 1 hydrogen because it has 3 bonds. Remember, carbon always wants 4 bonds. And then this carbon over here gets, each carbon wants 4 bonds. Sorry, not each hydrogen. Each carbon wants 4 bonds. This carbon down here gets 3 hydrogens. So this would be your ending structure. You might see it written like this as well. One thing to note, do you see how this line is reaching out to the chlorine? That line is encompassing the chlorine, okay? There's no carbon here. Same thing with this. This line is including the bromine, like the bromine, this is a packet. So there isn't a carbon sitting here. So sometimes what people will do is they'll see this structure and they'll go, oh, there's 1, 2, 3, 4, 5 chlorines. No. This is, I'm sorry, 1, 2, 3, 4, 5 carbons. This is a carbon, this is a carbon, this is a carbon, and this is a carbon. This line at the tip here, if there's a chlorine written on it, it's a chlorine, it's not a carbon. If this happened to not be here, then we could assume that that's a carbon, yes. But if it's got the line pointing at something that isn't a carbon, keep that together, okay? So this has 4 carbons. Okay, name each of the following alkanes. So that's getting like real skeletal for you. So, but hopefully you're starting to see, oh, there's carbons there. That's a carbon, that's an accessory. So draw them out and then name them. I'll give you 2-3 minutes for that. Okay, so find the longest carbon chain for each of these. So this top one is 1, 2, 3, 4, 5, pentane. The bottom one is 1, 2, 3, 4, 5 as well. So it's also pentane. If you had counted off of this one, 1, 2, 3, 4, 5, it'd still be 5 either way. So both are pentanes. We want to number them in such a way that the accessories land on the lowest numbers. So for the first one, it'll actually be counting from right to left. 1, 2, 3, 4, 5. B, it'll be left to right. 1, 2, 3, 4, 5. So for this first one, we've got our chloro accessory landing on the second carbon. So it'll be 2-chloro-pentane. This one has multiple accessories, specifically multiple methyl accessories, and they land on the 2 and the 3. So 2,3-dimethyl pentane. So both pentanes, but the top one has a chloro on the second. The bottom one has 2 methyls on the 2 and the 3. Questions on that? Okay, so let's go with, excuse me, properties of alkanes. So different uses of alkanes and alkane compounds result from the physical properties, specifically their density and their solubility. Solid alkanes, like the one that they put on these apples. So if you didn't know, those apples look so shiny and delicious because they're covered in a waxy coating. You're actually better off getting the apple that doesn't look so shiny. Why do they put this on here? Well, it helps to prevent mold and retain moisture in the apple. It creates more of a preserved apple. It's not bad. I mean, you can eat it and digest it, but if you're looking to minimize the amount of alkanes you're consuming, you may want to get the one that doesn't have it. So in general, alkanes with 1 to 4 carbons will be gases at room temperature. They're super light, right? They don't have a lot of carbon chains, so they're kind of airy. They float around. So methane, ethane, propane, and butane are all going to be gases at room temperature. If we're at 5 to 8 carbons, that's pentane, hexane, heptane, and octane. Those are all highly volatile liquids at room temperature. That means they're really good for fuel. Highly volatile means that they turn into a gas pretty easily. So if you've ever spilled gasoline on your hand, it seems as though the gasoline is no longer there, right? You dry your hand off and you get in your car and you can still smell the gasoline. That's because it's volatilizing off of your hand into your nose. If you have an alkane with a chain of 9 to 17 carbons, these will be liquids with much higher boiling points. They're not so volatile. They tend to stay as liquids. So things like motor oils, mineral oils, kerosene, jet fuels, heavier carbons. Here's a decane. If you have an alkane with 18 or more carbons at room temperature, these are known as paraffins. So if you've ever seen on the back of like a beauty product, it says, contains paraffins, or you have some conditioner that says doesn't contain a paraffin. Well, what's a paraffin? It's just a general word for an alkane group that's 18 or longer. Petroleum jelly and Vaseline is a semi-solid mixture of hydrocarbons with more than 25 carbon atoms. Okay, so as you add carbons, as your chain gets longer, you're going to move towards the solid form. Solubility and density of alkanes. In general, alkanes are nonpolar. They're insoluble in water. They're less dense than water. They're flammable in air, and they're found in crude oil. So here is a stunning picture of an oil spill. We have water, and then there's the oil floating on the top. Fortunately, the oil is less dense than water, so we can actually kind of scrape or sieve it off the surface for cleanup. It would be really bad if the oil was more dense and sunk down to the bottom of the ocean. So we've got, so that was in April 2010, there was an explosion on an oil drill rig in the Gulf of Mexico. This was an extremely, extremely devastating oil spill. largest in US history. To give you an understanding of how much oil, 10 million liters of oil per day were being leaked into the ocean, into the Gulf. There's a couple different ways that we can clean up. Mechanical, which is where they use a big boom and they just sort of skim or like collect the oil mechanically. Chemical, which is where they use some sort of substance that, like a non-polar substance that attracts the oil, and then they can scrape it up in recovery tanks. And then this one, which has been explored more recently, which is really cool, is a microbial or microbiological mechanism, which is there are certain bacteria out there that actually like to ingest oil, and they can eat the oil that's spilled and break it down into less harmful products. So let's look at a general combustion of an alkane. This shouldn't be too revolutionary for you since we've already gone over combustion, but alkanes have these strong carbon-carbon bonds. They react with oxygen, right? All combustion reactions are carbon reacting with oxygen to produce CO2 and H2O. There's a release of energy when the carbon-carbon bonds are broken. Methane is a natural gas that we use to cook our food for the most part. Combustion of butane. So butane's a little bit different than what we had going on here with methane. Methane, we had 1 carbon. Butane, we have 2 carbons. Or I'm sorry, butane, we have 4 carbons. And when we balance it out stoichiometrically, 2 butane molecules will combine with 13 oxygen molecules to produce 8 CO2s and 10 H2Os. We use this. Butane a lot of times are used in portable burners because you get a lot more bang for your buck. There's more carbons in there. There's more energy produced, so you don't have to bring such a big canister. Study check. Okay, I want you to write a balanced equation for the combustion of propane. C3H8 follows the same rules that you've known about combustion this entire semester or the last, month or 2 of the semester. Okay, I'm going to keep moving forward just because we do have some other things to look over. So propane is C3H8. If it's a combustion reaction, it always combines with oxygen. So C3H8 plus oxygen. It will produce CO2 and H2O. From there, we want to balance it. So you always balance the carbons first. Then, then balance the hydrogens, and then balance the oxygens. So it should be one of these. 5 oxygens rather gives us 3 CO2s and 4 waters. So does it get more complicated than what we've talked about? Obviously. So the next thing we're going to look at is alkenes and alkynes. Now, up until this point, I've said, hey, everything in the carbon chain is single bonded to each other. Well, that's not always the case. We can have situations where we have an alkene, E-N-E-S, alkenes. This is where there is some sort of double bond. And the double bond is happening between carbon and a carbon, okay? An alkyne with a Y-N-E-S ending is when there's a triple bond. And again, the triple bond is happening between carbons. So it'll be a carbon triple bonded to another carbon. So this right here is known as ethyne. Eth, because it is how many carbons? 2 carbons, right? YNE, because it's triple bonded. They each only have 1 hydrogen on the end because the other bonds are being occupied in the triple bond. So we will go over all these. Alkenes and alkynes respectively contain a double and a triple bond. Sometimes they're called unsaturated hydrocarbons. Okay, the single bond ones, we call those saturated hydrocarbons because they have the most amount of hydrogens that they can possibly have. Alkenes and alkynes are unsaturated hydrocarbons because they don't contain the maximum number of hydrogens. Looking back at this picture here, if this was just ethane, it would be carbon bonded to carbon and it would have 3 hydrogens on each carbon. Okay, this is ethane. But because ethyne has a triple bond, that means that the open slots for the carbons being occupied with the bond, they can only have 1 hydrogen on each side. The saturated would have 3, the unsaturated would have 2 or 1. These guys are very reactive with hydrogen gas. They can react with hydrogen gas to increase the number of hydrogen atoms and then transfer into an alkane. And I'll show you that structure a little bit later. So identifying alkenes. An alkene contains 1 or more carbon-carbon double bond. So here's ethene. In ethene, we've got C2H4, 2 carbon atoms are connected by a double bond. This is a little bit different as far as its arrangement. Remember with ethane, it had 3 carbons sticking off of it, so its structure was tetrahedral. Here we've just got 3. We've got 1, 2, and then 3 groups. 3 groups give us 120 degrees between each, which we would say is a trigonal planar arrangement. Now, one thing I want to tell you about this, and we'll get into it with cis and trans, but the double bond, think of the double bond, it's stronger than the single bond. You can't rotate or twist on a double bond, okay? There's no rotation. So remember with the single bond, you could draw a structure in a bunch of different ways and it would all be the same thing, the alkane, right? We could, because we know that it's rotating on the single bond. That rotation no longer happens with a double or a triple bond. If you have this structure here, and let's say that this was a chlorine and this was a chlorine on opposite sides, it's frozen like this. You can't rotate so that the chlorines are on the same side. So some things about ethene, sometimes more often referred to as ethylene. It's an important plant hormone. It helps to ripen bananas, accelerates the breakdown of cellulose in plants. Alkynes contain 1 or more carbon-carbon triple bonds. So in ethyne, C2H2, we have 2 carbons that are triple bonded to each other. So 1, 2, 3. And they each just have 1 hydrogen because they only have 1 open spot for a hydrogen. As far as the structure is concerned, where the other one made little tetrahedrals, the alkane made tetrahedrals, the alkene made little trigonal planars, this makes a linear structure because I have 1 group here and 1 group here. These are going to be 180 degrees away from each other. The electron groups want to get as far away from each other as they can. So identify each of the following as an alkene or an alkyne. That's all you have to do for right now. I'll teach you how to name it later. Not later, like in 2 minutes. First one, this is going to be an alkene, okay? You see how there's 2 lines parallel to each other here? That is representing the double bond. Over here, this would be an alkyne. These 3 lines are representing a triple bond. As far as where the carbons are, because sometimes they'll draw, what is that? Sometimes they'll draw it with a kink like this. So there's a carbon here and there's a carbon here, clipping the ends. Sometimes they draw it as a straight line. There is a carbon here and a carbon here, kind of closing off the triple bond. So sometimes it is made as a straight line, but you will put sort of a truncation carbon right there.
Is there a carbon then at that next kink after the end of the line?
Here?
Right, yeah.
Yeah, so we would say carbon, 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 and then follows the rules that you're used to of where the kinks are. So as far as naming these things, okay, it's similar to naming alkanes. You use the alkane name with the same number of carbon atoms, but you replace the ANE ending with ENE if you have a double bond, and you would replace the ANE with the YNE if you had a triple bond. If you have a cyclical alkene, so you have like a cyclohexene, you would just change the N to ENE as well for the double bond. So this over here is ethane with a single bond, right? What if instead of a single bond, it was a double bond? We would call that ethene. What if it was a triple bond? We'd call it ethyne. There are these other names. I'm not going to test you on those, okay? If we have propane, what if we have a double bond? We would call it propene. What if we had a triple bond? We'd call it propyne. You see how the double bond and the triple bond is happening on a carbon that, like, there's only one place to put it right here. The double bond can only go here. The triple bond can only go between these two carbons. Down here, the double bond is always happening between carbon 1 and carbon 2. Here, the triple bond is always happening between carbon 1 and carbon 2. When you get to a chain longer than 3, you will have to tell me number where the double or the triple bond is. So guide to naming alkenes and alkynes, name the longest carbon chain that contains the double or the triple bond. This is important. In organic chemistry, there's this thing called precedence, or kind of what's more important. A double bond and a triple bond is more important than one of those methyl accessories. So even if there's a longer chain that you could make without the double bond, you need to make the longest chain that contains the double and the triple bond, because that is more important than just having the longest possible chain. Does that make sense? So it has to be the longest chain with double and triple bond. Are there things that are more important than double and triple bonds? Oh yeah, there are all these other functional groups that take precedence or are more important, and you would number off of those versus the double and the triple, but we're not there yet. So number the carbon atom chain starting from the end nearest the double or the triple bond, again, because they take precedence over the accessories. So if you are like, well, I could number it the other way to get a lower number for my fluoro or chloro or methyl group, you don't do it. You always want to put the double and the triple at the lowest carbon. Give the location and the name for each substituent after that as a prefix to the alkene or alkyne. So that happens at the very end, almost like an afterthought. So let's look at this one here. So in this one, I'm finding my longest carbon chain with the double bond. So first identify the double bond. Here it is. The longest carbon chain, 1, 2, 3, 4, 5 carbons. All right, and there is a double bond. Now I need to number them. So before, you guys would have probably been like, oh, I would name this carbon 1, 2, 3, 4, 5, because that would put this at 2 and that would put this at 3, right? But this is the most important thing in the chain, so we always want to number that way. So I'm going to go with this being 1 and this being 2, 3, 4, 5, because that puts the double bond at the 2. So the double bond is happening from carbon 2 to carbon 3. You will call this a 2 though. You don't call it a 2-3. So we would say that this is pentene. right? There is a double bond. It's happening at the 2. So 2-pentene. Always put it on the lowest number of the bond. If it was at the 3-4, you would say 3. If it was at the 7-8, you would number it 7. So now we've got the base. We need to add our accessories. So the only accessory here is that methyl group, right? This thing right here, and that's on 4. So 4-methyl-2-pentene. Sometimes you may see they take the 2 and they stick it in here. So it would be like 4-methyl 4-methyl pent-2-ene. Okay, so sometimes they stick the 2 in there. I'm not gonna do it that way, but you may see that online or somewhere. And if you see that, just know that this 2 is supposed to be the 2 in the front. It's saying, hey, it's 5 and there's a 2 double bond or a double bond at the 2. So just be aware that that could happen. This second one here. Okay, so we have, well, we really only have one chain, right? 1, 2, 3, 4, 5, 6. I'm going to number it from this end. 1, 2, 3, 4, 5, 6. 6 is hex. It is got a triple bond, so it's hexyne, Y-N-E. And we just need to specify where the triple bond is, 2-hexyne. Yes? No? Yeah? Okay. Give the accessories. Okay, so what if we have a cycloalkene, a cyclical one with the double bond? The double bond, again, always takes precedence against any accessory or arm. So we would always have the double bond, or, well, you wouldn't have a triple bond. We'd always have the double bond start at carbon 1. And then we count until we get to our accessory in the lowest number possible. So for this one, this is carbon 1, 2, whoa, hello, 1, 2, 3. This is hexene, cyclohexene. We don't need to say that the double bond is on 1. We don't need to say 1 cyclohexene because we're going to just always put the double bond on the carbon 1, but we need to add this thing here, which is a methyl group, right? So 3-methyl cyclohexene. So I want you to name the following 2 things. It says, name the following alkenes and alkynes. Okay, well, they're just alkenes, so name those 2. All right, so this first one here, it's a ring. There are 6 carbons. So it's cyclohexene. Do I need to say that it's on the 1? No, I can just call this thing cyclohexene. This guy over here is 5 carbons with a double bond. So this is cyclopentene. I am going to number these because I've got an accessory, or 2 accessories really. This is carbon 1. I'm not going to go 1, 2, 3, 4 in this direction because that would put this at 4, right? Instead, I'm going to go the other way, 1, 2, 3, because we're always trying to make the numbers the lowest. So this is a methyl and this is a methyl group. They're both on 3, so 3, 3 dimethyl. And then what did we say it was originally? Cyclopentene. Again, we don't need to say 1 cyclopentene because it's always going to be on the 1. Are you guys having so much fun with this? It kind of makes the inorganic naming like a piece of cake, right? When you just flip-flop charges. There's a lot more rules to this. So when you have a double and a triple bond, because they can't rotate, you can actually get the same formula. The atoms are set up in the same arrangement, but they are known as cis and trans isomers, which means that the arrangement is just slightly different. Cis is when you have 2 similar limbs on the same side. So the thumbs are pointing on the same side. Trans is when they're on the opposite side. So you have to, in some instances, you'll have to identify it as a cis or a trans isomer. Let's look at these here. So this is 1,2-dichloroethene. Now, 1,2-dichloroethene could be either cis 1,2-dichloroethene or trans 1,2-dichloroethene. When it's drawn like this, don't get freaked out. You can't tell if it's cis or trans, okay? But if I said, hey, which one of these is the cis or which one of these is the trans, you would be able to write it. Cis, in this case, it's the limb at the end that is the same. So the cis would be where we have chlorine on both sides. Or it creates sort of like a, sort of like a boat. So like this over and up. Trans is when your accessory or your limb is on the opposite side. So here we're going like this, cis. Here our kink is going down, that is trans. That's important because I can't rotate. These are actually different. They have different properties. They're very similar, but they have slightly different properties. I cannot rotate this thing to get this. Why? Because the double bond is frozen. All right. If this was a single bond instead of a double bond, let's say that this was just one bond like this. This could easily rotate. These would be considered the same thing. But at a double and a triple bond, those are actually different isomers. So cis pointing on the same side, trans pointing opposite sides. If we look at butene, butene has specifically 2-butene, which has its double bond in the center. We can have cis-2-butene. Do you see how it's pointing up? Same side. And then trans is when you make the opposite side sort of jagged shape. So it is important to be able to identify cis and trans. Just so you know, as far as like FYI, for cis and trans, many insects imitate minute quantities of chemicals called pheromones to send messages out to others of the same species. And these are usually, they have to do with cis and trans. Pheromones may warn an insect of danger, mark a trail, or attract the opposite sex. The effectiveness of many pheromones depends on the cis or trans configuration of where the double bond is happening. So let's see, when looking at this, the prefix for this one we would say is cis. The prefix for this one would be trans. It did it for us. All right, so I want you to look at these. You're going to need to name it. So find the longest carbon chain, add the accessories, and then classify it as either cis or trans when needed. All of these will need a cis or a trans. Okay, so all of these are some sort of form of 2-butene. 1, 2, 3, 4 carbons, 1, 2, 3, 4 carbon, 1, 2, 3, 4 carbon chain. The double bond is happening from the 2, 3. So they're all 2-butenes. They have, some of them have accessories. This one here has 2 chlorines. So it's a 2,3-dichloro. This is a 2,3-dibromo. This doesn't have any accessories. This is just 2-butene. This top one here is a cis, right? Because the chlorines are on the same side. The second one is a trans because it has the bromines on the opposite side. This one here, see, we would call this a trans because like the hydrogens and the carbons are on the opposite side. So all butenes. Questions on cis and trans? You don't need to do cis and trans for alkanes, single bonds. Okay, I've got just a couple minutes left, so I'm just gonna go through a few other things. Addition reactions. Look at all this yummy hydrogenated oil stuff, saturated fats. So there's a commercial process of hydrogenation, which is used to take fats that have double bonds, you shove them with hydrogen and you make saturated fats, or you make you stick a bunch of hydrogens on there and get rid of the double bonds. So alkenes and alkynes, what you can do is you can take the double bond and you can actually open it up and then shove hydrogens onto it. Very reactive. You can add hydrogen or you can add water to the carbon in the double and triple bonds. They're easily broken, and you can provide, you can produce new things. So hydrogenation is when you add hydrogen. So you take an alkene, you add hydrogen, and you get an alkane. Hydration, which is a little bit different, is when you take an alkene, you add water, and you get what's known as an alcohol. We haven't talked about alcohols yet, but we will in the next chapter. This is what hydrogenation looks like. And you will have to be able to like identify this. So do you see how you've got an alkene right here, a double bond? Well, if I add hydrogen to it and then you use some sort of catalyst, usually it's like a metal, this double bond will open up so that you have 2 limbs on each side and you'll stick hydrogens on it. If you have a triple bond, you can open up 2 of the bonds. So this bond, and you'll have 2 limbs on each side to shove hydrogens on. It looks something like this. It's kind of hard for me to draw it in this here, but come on. Everything's just freezing up on me. So again, let's say I've got ethene. And if this has 2 bonds already in the double bond, this has, you know, a hydrogen here and a hydrogen here, and this has a hydrogen here and a hydrogen here. Well, in the process of hydrogenation, not hydration, hydrogenation, we add hydrogen. And what goes on is this double bond goes away. So it's kind of like we've erased it to make a single bond, but carbon always wants to have what? It always wants to have 4 bonds. So it is going to open up slots for those hydrogens to get shoved into there. And now what do we have? It was an ethene. Now it's ethane. It went from an ene to an ane. We got rid of the double bond. The same thing can happen with a triple bond as well. So for this, write an equation for the hydrogenation of 1-butene using a platinum catalyst. Ugh, we're over time-wise. I'm gonna just do this really quickly, okay? So if it's 1-butene, that means we have carbon, double bonded to a carbon, single bonded to a carbon, single bonded to a carbon, because the double bond is on carbon 1. I'm going to add my hydrogens, H3, H2. This has 1 H and this has 2 H's. If we undergo hydrogenation, that means we're going to add hydrogen. It says it's got a platinum catalyst, right? So I'm just going to put PT above the arrow. That lets me know that there's a platinum catalyst. I'm going to open this up, bing, bing, so that there's going to be 2 limbs here. And what I'll end up with is a carbon chain where they're all single bonded and it's saturated. So instead of this having 2 hydrogens, it now has 3 hydrogens. Instead of having 1 hydrogen here, we now have 2 hydrogens, and we've become butane. So this is the process of hydrogenation. When you hear about hydrogenated oils, this is what they are doing. A little cleaner appearance of it, yeah. So we take that double bond, we pop it open, and we shove some hydrogens on it. Okay, unsaturated, now it's a saturated fat. Okay, that is the process of hydrogenation. We will go over this next week, and then we'll get into alcohols. There's one other reaction. Oh, I do really quick. Sorry, guys. I do want to tell you about an aromatic, just for homework's sake. So an aromatic is anything that contains a benzene ring. This was discovered, well, it's always discovered by multiple people, but Michael Faraday was able to isolate this benzene ring. It can be written in a couple different ways. It's a ring of 6 carbons and it has 3 double bonds, okay? And the double bond is every other position. Sometimes it's drawn like this. You can see that the double bond it can be drawn like this, because this double bond is actually sort of moving into this spot, and this double bond is moving into this spot, and this double bond is moving into this spot. So it's sort of rotating around these 3 double bonds. So because this is always sort of rotating, sometimes the benzene ring or the aromatic can be drawn as a circle like this. This is not the same thing as hexane. People sometimes will get this mixed up with cyclohexane. Cyclohexane is 6 carbons, all single bonded. If it has the circle in the center, it is benzene. Okay, the circle lets you know that there are 3 triple bonds that are oscillating around it. This is a very, very important compound. It is in all sorts of different things. And if you're wondering, aromatic, isn't that about smell? A lot of things that have strong odors and smells to them contain aromatic rings in them. Okay, so we will leave it at that for now. If you have any general questions, throw it out there. If you have a personal question, stay around. Sorry, I went over a couple minutes. Appreciate it. I will see you all next week.